Hello, welcome to Maths with EJD. In this video, we are talking about measures of dispersion or variability. In previous videos, we already talked about measures of central tendency like mean, median, and mode. Afterwards, we talked about measures of position like percentiles, deciles, and quartiles. So here, our focus shifts to dispersion, measures of dispersion or variability like range, interquartile range, variance, and standard deviation. So come along. Of course, if you have not subscribed to this channel, be sure to do that right now. And of course, hit the notification bell so you can always get alerted when a new video is released. So measures of dispersion or variability. Let's go. Measures of dispersion help us understand how spread out the data is. So whatever data you're working with, you want to know how spread out it is. So, measures of central tendency or location, they are single values that are used to represent the whole data, whereas measures of position tells you the position of a particular value in the data. But measures of dispersion help you to see, okay, so if we have the mean of a data, how far away is each value in the data from that mean and all that? So that's what measures of dispersion or variability are about. So they help us understand how spread out the data is. And these include the range. You have the range. You have variance. You have standard deviation. And then you also have standard deviation, right? You have standard deviation, and then you have interquartile range, IQR, interquartile range. Okay, interquartile range. So these are the measures of dispersion of variability. Okay, let's take them one after the other and see what we can do with them. Let's go with range first of all. Range. Okay, has a very simple definition. The range of a set of data is simply the difference between the maximum value and the minimum value. Simple. So range is maximum value minus minimum value. That's all. Okay. Now, if you want to calculate range for ungrouped data, see what you have. Ungrouped data. Of course, the definition is as simple as it gets. So if you have this data set 12, 15, 8, 21, 10, 14. Of course, you don't need to arrange this in any particular order. All you just need to be able to do is to be able to identify the maximum value. So the maximum value in this case is obviously 21. And then you also need to identify the minimum value. The minimum value in this data is obviously 8. The minimum value is 8. So given those two, you can simply calculate the range to be 21 minus 8, and that is 13. So for this data set, the range is 13. Okay. So how do you interpret the range for a data? Interpretation. So the range of 13 shows that the data value, the date shows that the data values spread over 13 units. Okay. The data value spread over 13 units. That's the range. So let's consider grouped data now. Grouped data. So for group data, imagine you have this class interval, and then you have frequency as usual. So the first class, you have 0 to 10, and it occurs 3 times. The second one, you have 10 to 20, and that occurs 5 times. And lastly, you have 20 to 30, and that occurs 2 times. Okay? So, of course, here, it may look like you need to do something big, but not necessarily. Minimum value comes from the lower boundary, from the lower boundary of the first class. And that is actually 0. So if you look, so the first class here, so of all these values, all these 0 to 10, it means you have 0, 1, 2, 3, 4, 5, 7, 8, 9, 10. The lowest there is 10. And on the other hand, right, so the minimum value is 0. And then on the other hand, the maximum value comes from the upper boundary, of the last class. So the last class here, you have 20 to 30, and 30 is the biggest there. So that's 30. So simply, range here is equal to 30 minus 0, and that is simply 30. So range is as simple as it gets, like I said. So interpretation, the data, so it means that the data spans 30 units in total. And that goes. Okay? That's about range. Now let's move on to variance now. Interestingly, variance and standard deviation move together. They operate together. But let's talk about variance first. So anytime you need to calculate standard deviation, you need to compute variance first of all, because standard deviation is simply the square roots of variance. Okay? So variance measures how much the data, points deviate from the mean. Okay? How much data points deviate from the mean. That is what variance measures. Okay. So, of course, when we started out with statistics, right, we had some key concepts like population, that's total population you're thinking about, and you have the sample, which is a portion of the population taken to study the whole population. So as a result of that, if you're thinking about variance, you're also thinking about variance for population, and you're thinking about variance for sample. So now let's talk about population variance. Population variance. So for population variance, now it's something like sigma squared equals 1 over n summation I equals 1 to n into xi minus mu all squared. Okay. So of course, xi will be the data points, while mu is the mean. So you can see the difference between each data point minus mean is, so this is a deviation on its own. So you square that and you sum up each item like that. And of course, at the end of the day, you divide by the total population. So here you say, so with this now, so where n is the population size, xi is a data point, So x1, for instance, is first data point, x2, second data point, and so on and so forth. So xi is a data point, and mu is the population mean. Mu is the population mean. Okay. So that's for the population. Can we talk about sample variance too? Sample variance. So a sample is a portion drawn out of the whole population to study the whole population, since most times you can't actually work on the whole population together. So that is represented using small s. So you have s squared equals, now mind you, because you are sampling, so you say 1 over n minus 1. So it looks like population mean, right? Except that here you have small n because it's a portion of the population you're taking, but minus 1. then summation I equals 1 to n. Same thing, xi minus x bar squared. Okay, so this x bar is actually is sample mean, while mu is population mean. You know, the other time we talked about parameters and statistics. So we have population parameters, whereas we have sample statistics. Okay, so x, we have that, right? And then so it's basically the same except for the a few differences. Like the instead of big N up there, you have small n minus one down here. And then instead of mu, you have x bar. So here, so where n is the sample size, as opposed to big N that was the population size, where n is the sample size, xi is a data point. Xi is a data point, and x bar is the sample mean. X bar is the sample mean. Okay. Now let's do that for ungrouped data first. Let's do variance for ungrouped data. Okay. So imagine you have this data set 6, 8, 12, 14, and 16. Okay. You want to calculate variance, right? Don't forget, in this case, right, it's we are, of course, this we can consider this as a sample, right? Except if if you're told it's the whole population. So in that case now, you need to use this formula. So it means you need to know n, you need to know the xi's are the values now. So this would be like this is like x1, x2, x3, x4, x5. So that simply means that n is equal to 5. So you have 5 data points. So what else do you need to know? You need to know x bar. X bar is the mean. So we can go for that, right? So we have, so step 1, calculate the sample mean. Calculate the sample mean, which is x bar. So that means x bar is simply, mean is what we've done that before under measures of central tendency or measure of location. So you have 6 plus 8 plus 12 plus 14 plus 16 divided by 5. 6 plus 8 is 14. 14 plus 12 is 26. 26 plus 14 is 30. 30 plus 16 is 46 divided by 5. So that is 46 divided by 5. That's actually, is that correct? 6 plus 8 is 14. 14 plus 12 is 26. 26 plus 14 is 40, actually 40. 40 plus 16 is 56. So that's much. So that is 56 divided by 5. And that is, it's easier to divide by 10. So 56 times 2. 56 times 2 is 112. That's my first way of dividing, divided by 10. So you can easily know this is 11.2. Or you can just punch your calculator and get 11.2. So the mean is 11.2. So that's the first step. Second step. So now you see we have got this x bar. So next thing the we need the square of the deviations. So what you have inside this bracket here is what you can call the deviation. That means the difference between each data point and the mean. Okay. So then you need to square that. So let's go for it. So point 2, you want to calculate the squared deviations. The squared deviations from the mean. From the mean. So that means you have, for the first one, you need x1 minus x bar squared. That is 6 minus 11.2 squared. So what you can punch your calculator and the answer is 27.04. Then next, this is, you already have x1 to be 6, x2 is 8. So next is x2 minus x bar, which is 8 minus 11.2 squared. So if you subtract you get something negative, but by the time you square, the answer comes to 10.24. And then you have x3 minus x bar, and that is, let me do that again, x3 minus x bar squared. That is, the third point is 12, right? So you have 12 minus 11.2 squared, and that is 0.64, because 12 minus 11.2 will be 0.8. 0.8 squared is 0.64. Then we have 14 now. That's like x4 minus x bar all squared. So that is 14 minus 11.2 squared. That is 7.84. Then lastly, you have x5 minus x bar squared. And that is, I mean, it's better. This is better done in a table, right? So it's better than in a table. So I'm going to do the table thing afterwards. So x5 minus x bar, that's 16 minus 11.2 all squared. And that is 23.04. 23.04. So we have all that now. So the next thing is, now from the formula, right, you know how to go. So we found x bar, so we found the deviation squared. So we now need to sum up everything and then later divide by n minus 1. So the next thing is to sum things up. So 3, you have to sum the squared deviations. Sum the squared deviations. So it means you have 27. Okay, I can write that symbolically. Summation from I equals 1 to n. All right. Summation from I equals 1 to n, of course, uh, of xi minus x bar all squared. That's what that is. So that means you have everything you've got, 27.0 for the first one, then 10.2 for the second. So 10.24 plus 0.64 plus 7.84 plus 23.04. Last, all of this together will be 68.8. When you check, so we have 68.8 there. So lastly, number 4, we divide by n minus 1, and that is 5 minus 1, which is equal to 4. So that at the end of the day, s squared is the summation from I equals 1 to n of xi minus x bar squared divided by n minus 1. Of course, that's the same thing as 1 over n minus 1 multiplied by that, so no worries. So this is 68.8 divided by 4. And the result is 17.2. So the variance of that ungrouped data is actually 17.2. Okay, 17.2. So the interpretation is something like this. The sample variance is 17.2. It's 17.2, meaning that on average, the data points deviate from the mean by 17.2 squared units. 17.2 squared units. Okay. Now, just like I said the other time, instead of having to work things out the way we've just done it now, it's more convenient, especially in an examination situation or in whatever situation for that matter, right? It's more convenient to do these things in a table format. So you could as well just have your xi, and then next you have, and you can compute your x bar by the side. Then you have xi minus x bar, okay? And next you have xi minus x bar all squared, and then other things can follow from here. So for instance now, so the first value, right, is actually, what is it now? 6, okay, 8, 12, 14, and 16. Okay, that's what you have. So instead of having to do it the way those step-by-step thing, that can be that can lead to a lot of confusion. So you can just make your table straight up, and then so once you make the table, the next thing you can, of course, you have to compute your X bar by the side. So your X bar is simply equal to 6 plus 8 plus 12 plus 14 plus 16 divided by 5. So that's X bar equals, what did we get the other time? That's 56 or something. Yeah, 56 over 5, 6 over 5, and that is simply 11.2. So you have your X bar to be 11.2. So all you just need to do is 6 minus 11.2. Okay. Of course, 6 minus 11. So it's more like 11.2 minus 6. That's 5.2, right? Yeah, that's 5.2. So that'll be minus 5.2. Okay. Minus 5.2. And then here, minus 5.2 squared. When you square this, is minus 5.2 all squared. And that is what gives you that 27.04. Yeah. You have 27.04. Of course, you don't have to write all these ones. I'm just explaining here. So 8 minus 11.2 is like 11.2 minus 8. Of course, because 8 is smaller than 11.2. So you have minus 3.2. So when you square 3.2, that's like 32 squared, right? That's why you have 1024. So that is 10 again. That's minus 3.2 squared. You have 10.24. Then for the next one, right? You have 12 minus 11.2. Now, this is bigger. So 12 minus 11.2 is now 0.8. When you square that, 0.8 squared, you have 0.64. And next you have 14 minus 11.2. That's like 14 minus 11 is 3 minus 0.2. That should be 2.8, I believe. 2.8. 2.8 squared is what gives you 7.84. 7 point, okay, that's 2.8 squared gives you 7.84. And lastly, you have 60 minus 11.2, that's 4.8. So 4.8 squared now, 4.8 squared is what gives you 23.04, right? 23.04. So what else do you need? You need to, so all these deviations, now you need to sum them up, okay? So you now need summation of all these xi minus x bar squared, okay? So just sum up all of them up. And when that summing is done, you just get the same thing like we got before, that 68.8. You have 68.8. Because you already know your n is 5, right? Because you have 1, 2, 3, 4, 5. So your n is 5. And you just go ahead and get your variance. Get your variance to be summation of xi minus x bar all squared divided by n minus 1. That's 68.8 divided by 5, which is 17.2, like before. So the table, doing it on the table actually is easier. So you just go straight to the point. So everything is in one place. So that's it for ungrouped data. So let's do something for grouped data. For grouped data, how do we go? So I'll just go for the table approach straight up, so we don't have to waste time. I guess I want to change colors at this point. So let's talk about grouped data. Grouped data. So here, imagine the class interval. So what I will call should I call this? Let me call it xi. Let me call it xi, and let's have frequency. Here we have 0 to 10. I think it's the same thing we used before. That's 2. We have 10 to 20, which is 3. And then we have 20 to 30, which occurs 4 times. So that now in this case, the formula is about the same thing, right? The formula is still the same. that the variance S squared, don't forget this is S squared now. That's the variance. So the variance S squared is still 1 over n minus 1, summation from I equals 1 to n of xi minus x bar all squared. So same. So here now, because we have a range, we have a class interval, which is our xi now. And this is what I've always called ci. So here now, we need a single value. Okay. So this is our class interval, which I call xi here. So we now need a particular x. Or can I call this xi? I'm wondering what I can call this. Let me just call it class interval. Just exactly what it should be. Let me call it class interval. So when I get the midpoint, then I just call that xi. So this is ci. Okay. So after the ci, I'm going to need xi. Okay. That's computing the midpoint. And after that, I'm going to need okay, I guess I need to move this formula elsewhere. Okay, so I can have some space. So after xi, we need xi minus x bar. Okay, that means we would have found x bar somehow using what we've always known. Then we have xi minus x bar squared. And that's about all we need from this table. Okay, so this. Now let's go. So you remember the idea of midpoint, right? So this will just be, say, 0 plus 10 divided by 2. And that is equal to 5. So 5 here. So next you have 10 plus 20 divided by 2. That's 15. Okay. And lastly, you have 20 plus 30 divided by 2. And that is 25. So you see 5, 15, and 25. So that is your midpoint. So we get all those midpoints. So the next thing is, so these are the x values now that we need to use 5, 15, and 25. But then we need x bar at this point. And in this case, since we have a frequency kind of thing, right? To get x bar, to get x bar is actually summation f of xi all over summation f. So that means we need summation f itself. That's the total frequency. 2 plus 3, 5. 5 plus 4, that is 9. Okay? That's the total frequency there. Then for the x bar now, okay, we need summation of f of xi. Okay. So I think we need to create a column for f of xi. I guess I can divide this into 2. So I can divide this into in fact fi, I can say fi xi. So fi multiplied by xi, and this will now be xi minus x bar. Okay. So here now we have fi xi. That is 2 times 5, 10, 3 times 15, 45. Okay. And then 4 times 25, that's 100. So that summation of fi xi will be the summation of all of this. 10 plus 45 is 55. 55 plus 100 is 155. Okay. Or better still, I want to use another color to make it stand out. Okay. So summation fi xi is 155. When you add 10 plus 45 plus 100, that's 155. Okay. So now we need the deviations. So we need xi we need the deviations now. Xi minus X bars. So X bar is 155. No, X bar. Okay, we need to compute X bar, sorry. We need to compute X bar. To compute X bar now, that means we have summation f of fix, so that's 155 divided by 9. 155 divided by 9. So that means we are going to have 155 divided by 9 as our average. So that, okay, in a moment, I'm going to get that. (155 over 9). Just a moment, please. 155 over 9 is what I'm going to get next. Yes. Yeah, 155 over 9 is approximately 17.22. In fact, let me change the colors so that it can be consistent and also stand out. Okay, so this is equal to 155 divided by 9, and that is approximately 17.22. So we need, this is our X bar now. So the next thing we need to do then is to find, so you see all these midpoints now, all these 5, 15, 25 will now be what we have here now. So we have, first of all, we need to compute the square deviations, but let's do the deviation first. So this is like deviation. So here, this is deviation square, deviation square. Deviation is the difference between the data point and the mean. Okay, so that means here we have 5 minus 17.22, and just like what we had before, right? That will be 5 minus 17.22. That's like 17 minus 5. That's minus 12.22. Minus 12.22 right there. Okay. 17 minus 5. Yeah, that's minus 12.22. Okay. So next thing is we have 15 minus 17.22. That is, of course, 2. That'll be minus 2.22 again, minus 2.22. Then we have, lastly, 25. Now this is 25 minus 17.22. Now 25 is bigger. So 25 minus 17 is 8, you know. Yeah, that's 8. So remove 0.22 from 8. That should be like 7.88 or something like that. That's 7.88. Yeah, 0. No, 7.78. Should be 7.78. Yeah. So 7.78. So when you square all that, right? So when you square this, now, if you square that, you get 149.66. When you square this, you get 4.93. When you square this, you get that square 7.78. When you square that, right, you get 60, 60, that's 60.57. So having done all of that, now, we can now put the values together. We can put them together now that we have 60.57. So another thing we still need to do is to multiply them by the frequencies, right? We need to multiply them by the frequencies. So it means we need In fact, in this case, I should have written out a separate kind of formula. I think I'm still going to have to do that. So we need to multiply by frequencies. That means we need we need the frequencies. That's Fi multiplied by Xi minus X bar all squared. So that would be 2 times 149.66. 2 times 149.66. That would be, so these two, I guess I also want to change. 2 times 149.66. That would be 299.32. 299.32. The next 3 times 4.93. 3 times 4.93. That is 14.79. Then lastly, 4 times 60.57. That is 242.28. Okay. Then we need the sum of all this now. So this is summation of f of I, xi minus x bar all squared. So when you sum all of that together, you should get 556.39. Okay, 556.39. Of course, we know n is the same thing as summation of f, and that is 2 plus 3 plus 4, and that is equal to 9. So we have all the parts together now. So the formula here, which I did not write from the beginning, but I mean, it's never too late. So the formula here now is this. We need the standard deviation, and that is from everything we have seen, right? That should be summation from I equals 1 to n of fi into f into xi minus x bar squared. Okay, so the product of fi of the frequency times the square of the deviation, all divided by, if you like, n minus 1, which is the same thing as summation of f minus 1. Okay, so this is the formula in this situation. So it's always very good to start with the formula so you can now follow the formula to get the components you need. So from everything we've got now, s squared is actually summation from I equals 1 to n is this value here, 556.39. We have 556.39 divided by n minus 1, that's 9 minus 1. So you have s squared equals 556.39 divided by 8. And it means that the standard deviation, the variance is actually 69.55 for that grouped data. So don't forget the formula. So now that frequency is attached. So you need to calculate x bar first, which is summation of fi xi all over summation of f i's. Okay, you need to do that first to get this, and then other things move on like that. Okay. So just look at the table. I mean, all of this require practice so that you can get used to it. Now you don't have to put all this extra, all these things I showed, all the 0 plus 10 over 2, because it will make the table messy. So you can just do, I mean, with a calculator, you can just go straight to the point and just compute and put the values as far as you know what to do. And to know what to do, the first thing is write down the formula. And from the formula, you can know, from this formula now, you know, the first thing you need the midpoint xi because you have an interval. So you know from this interval, you need xi, which is the average of the smallest and biggest in the class divided by 2. Then next, you need to find a mean, So you find xi, you find the mean using this formula. The next thing is that you need to find their deviations. So xi minus x, then you need to square them. Then once you get the squares, you now multiply by the frequencies, each 10 by 10, and then you sum everything together and now divide by n minus 1. Okay, so that's all that for variance. And just like I said before, variance is closely related to standard deviation. So let's think. So it means that we don't have to do so much to talk about standard deviation because standard deviation is simply the square root of variance. So for standard deviation now, okay, for standard deviation, we can say that the standard deviation is the square root, of the variance. It is the square root of the variance. So it represents the average deviation. The average deviation from the mean, the average deviation from the mean in the same unit, as the original data. The same unit as the original data. Okay. So the formula is simply like, so the formula is like this. Sigma equals, so the standard deviation, sigma equals square root of sigma squared. That is for population. So when you talk about population, that's standard deviation for population. Whereas S is square root of S squared, and that is for sample. In fact, for sample, we call it standard error, not deviation per se. Okay. So let's do this for ungrouped data. Say ungrouped data, first of all. Just like what we had before, right? We can just invoke that. So from the ungrouped data we used before, we can just say from the data set, 6, 8, 12, 14, 16 with variance S squared, which is equal to 17.2. The standard deviation is S, which is square root of S squared, and that is square root of 17.2, and that is approximately 4.15. So it means the standard deviation for this data is 4.15. So the interpretation, which is really important, interpretation is something like this, that the standard deviation of 4.15 means that on average, the data points differ. Data points differ from the mean by about 4.15 units. So if, for instance, the data you have is the score of students in an exam, so you can say that the average that on average now the score of each student is about 4.15 scores, 4.15 units away from the average. Okay, so that works. Now let's talk about grouped data. Thankfully, we've done variance for that same group data, so we can just take the square root of that and we're good. So for the same group data we worked on, where we got standard variance rather to be 69.55 from the same group data, this 0 to 10 to 10 to 23, 20 to 34 from the same group data. So you can say for the grouped data, the sample variance is S squared, which is 69.55. So the standard deviation is S, which is square root of 69.55. That is approximately 8.34. So this tells us, so we can say therefore the standard deviation of 8.34 shows shows the data is more spread out, compared to the ungrouped data. Okay. So that's that about standard deviation. Now let's talk about interquartile range. Interquartile range, that's the last of the measures of dispersion of variability. Interquartile range. Before now, we talked about quartiles under measures of position. Talks about quartiles, which divides a data set into four equal parts. So here, the interquartile range is actually a measure of dispersion. Let's see. The interquartile range measures the spread of the middle 50% of data between the first quartile, Q1, which we talked about in the previous video, and third quartile, Q3, third quartile, Q3. It is useful for identifying the central spread, and outliers. In economics, people talk about the fact that the middle class is very important in determining how the wealth of a nation is. So if you have all the data of the wealth indicators, right, for a particular country, so the interquartile range will be like that that thing that tells you about the spread of the middle class of that nation. Okay, though this is an idea from data, but I think it is analogous in that sense. Okay. So what's the formula for interquartile range? The formula is simply this, that interquartile range is equal to third quartile minus first quartile. And of course, we had that taken care of previously, but I'm going to repeat that here now. So let's talk about interquartile range using ungrouped data first, and then we'll use group data later. So for ungrouped data, if you remember, we had an approach before. So if you consider the data set 2, 5, 8, 10, 12, 15, and 20. So that's simply n equals 1, 2, 3, 4, 5, 6, 7. So n is actually 7 here. Okay. So now how do we calculate Q1? That's the first quartile. That will be first quarter, that's 1/4. Okay. 1/4 times n. 1/4 times n times n plus 1. Yes, I think I remember that now. 1/4. So the first quartile is 1/4 times n plus 1. Okay. And that is usually position, the position, right? So that will be Q1 equals 1/4 times 7 plus 1 position. So in the data now, so Q1 is equal to 8/2, 8/2 to position, no, rather 8/4 to position. Okay, interestingly, this is second, right? So so Q1 is actually the value in the second position. So the value in the second position is simply 5, okay? So it means that Q1 is simply 5. So the lower quartile for the data is actually the value 5, easily. And then for Q3, so talking about Q3 now, you have Q3 again is 3/4 times n plus 1. And that is still talking about the position. Okay. So that means we have Q3 to be 3/4 times 7 plus 1, which is 8 position. So that is 4 here is 1, 4 here is 2. So it means that the third quartile is the sixth position data in the data set. So Q3 is simply so Q3. So now we see this is Q1 already. So 1, 2, 3, 4, 5, 6. So Q3 is 15. So 15 is the third quartile. So this is 15. So now interquartile range Q. Okay. So we can say therefore IQR is equal to Q3 minus Q1, which is 15 minus 5. So the interquartile range here is 10, simply 10. So that's just that. We can interpret that interpretation. The interquartile range of 10 shows that the middle 50% shows that the middle 50% of the data, the middle 50% of data is spread across 10 units. Okay. So that's more like if the data you had was probably in terms of their wealth, so you can say maybe they are spread across $10 million or whatever. It all depends on the context we are considering. And that is for ungrouped data. Can we do for grouped data? So let's go for grouped data now. Grouped data. So for grouped data, imagine we have a class interval, and then we have frequency. And here you have 0 to 10 occurring 4 times. You have 10 to 20 occurring 6 times. And lastly, you have 20 to 30 occurring 3 times. Okay. So we need the cumulative frequency distribution, right? Because we know already that whatever we are looking for, we need Q1 and Q3. So in this case, Q1, should I use this? Q1 would simply be the lower boundary of the first quartile class, which we are going to compute, right? The lower boundary of the first quartile class plus n times 1 over 4, because first quartile is 1 over 4, minus the frequency, the cumulative frequency before that class, multiplied by the class width divided by the frequency, divided by the frequency of the first quartile class, actually. So again, don't forget, this is lower boundary of first quartile. Let me just say Q1 class. Q1 is meant for the class to which Q1 should belong. That's the Q1 class. Then this is total frequency. If you add all the frequencies together, that is what N is. And this is cumulative frequency before the Q1 class. This is the class width. H is the class width. That's the difference between the smallest value and the biggest value of each class. And small f here, this can always be a confusion. This is small f. So this small f now is frequency of the Q1 class. Frequency of the Q1 class. So if you are doing it for Q3, it's the same format, except that now we have n times 3 over 4 inside the bracket, and then the class will be most likely different. Okay, so to take care of this now, okay, let me just do something. Let's calculate the cumulative frequency. All right. Say we have Okay, let's say we have what I can call CI. We have CI, we have F, and we have CF. CF is cumulative frequency, by the way. So you have 0 to 10 occurring 4 times. You have 10 to 20 occurring 6 times. And you have 20 to 30 occurring 3 times. Okay. So if you want to do the cumulative frequency, of course, this is 4. Then next 4 plus 6 will be 10. Then 10 plus 3 will be 13. Okay. So for the first quartile class now, I mean for Q1, so we say Q1 is equal to, let me change colors here. It'll be finicky. So Q1 is actually, now, before we even find Q1, right, we need, okay, let me do it this way. Let me say for Q1, right, of course, we know that generally N is equal to 13. This total cumulative frequency is 13. So for Q1, so to get the Q1 class is determined by 1 over 4 times 13. That's 13 over 4. So 13 over 4, right? That's 13 divided by 4. So 4 in 13 is 3. Okay. Remember 1 over 4, that's 3.25. So the question is, and that's for, this is 1 over 4 n now, 1 over 4 times n. So it means that where does the cumulative frequency of 3.25 lie? So this is 4. So it means 3.25 is swallowed here. So it means that the Q1 class, so this 3.25 now, this implies that 0 to 10 is the Q1 class, okay? To the Q1 class. So now that we know the class, we can now calculate Q1. So the lower boundary of 0 to 10 is 0 plus n times 1. N is already 13 times 1 over 4 minus the cumulative frequency before the Q1 class. Of course, there's nothing before the Q1 class because this is the first cumulative frequency and which tallies with the Q1 class. So the cumulative frequency before the Q1 class is simply 0 times the class width. Okay, H is simply 10 minus 0 or 20 minus 10, which is 10 simply. Okay, so that's 10 divided by the frequency of that class. The frequency of the Q1 class is actually this 4 now. So this actually becomes 4 here. So we have Q1 to be 0 plus 13 over 4 minus 0 times 10 over 4, like this. Okay, so that our Q1 is basically 130 over 8. 130 over 8. 130 over 8 is 65 over 4, right? So 4 in 16 is 1. 4 in 25 is 6. Am I getting that right? Am I getting that right? 130 over 8. Just want to use it. I want to be very sure. 130. Oh, sorry, 130 over 16. Sorry. Oh, sorry. My mistake. I was wondering what was happening. So this is 6. So that's okay. Let me just go slowly. So Q1 is 130 over 16. That is 65 over 8. So that is 8 in 65 is 8, right? That's 8 whole number 1 over 8. That is simply 8.125 or something. So that is 8.125. So Q1 is 8.125. Settled. Then we now need Q3 again. Q3 is the third quartile. So again, we can say for the Q3, for Q3, right? More like for Q3. So the Q3 class is determined is determined by 3 over 4 times n, which is 3 over 4 times 13. That is 39 over 4. Excuse me, 39 over 4 is 4 in 39 is actually 9, right? 4 times 9 is 36. 3 over 4, that's 9.75. So it means where does 9.75 lie for the cumulative frequency? So coming back to the table now, you'll see that 9.75 is 9.75 will be here. So it means that the third quartile class is 10.20. Okay. I mean 10 to 20 rather. So this implies that the Q3 class is 10 to 20. 10 to 20. And so once you have that class, you can now calculate Q3 to be lower boundary of that class, which is 10 plus n times 3 over 4 being the third quartile class, minus f, the big F, the cumulative frequency before that class, times the class we divided by the frequency of that class itself. Okay, so it means that Q3 is equal to 10, the lower boundary of the third quartile class, plus 13 times 3 over 4. 13 is the total cumulative frequency, like we keep saying. Then minus the cumulative frequency before this class is actually 4. Okay, 4 again. So that is 4 times the class width we know is 10. The frequency of that class itself, the frequency of the third quartile class is 6. Take note, it's not 10, it's 6. 10 is the cumulative frequency, but 6 is the frequency of that class itself. So this is 6 now. So we can tidy all of this up to get our Q3. So we have Q3 to be 10 plus 13.3 over 4. I think we got that before to be 9.75. So this is 9.75 minus 4 times 10 over 6. 10 over 6 is the same thing as 5 over 3, I believe. Yeah. Then Q3 is 10 plus 5.75 times 5 over 3. Okay. So Q3 now is equal to 10 plus 5.75 times 5 over 3. In short, everything. Oh, okay, let me take the pen to be sure everything is in order. So 5.75, 5.75, 5.75 times 5 divided by 3. That is, so that would be, what is it? 9.5833. 9.583. So that's 9.5833. So that the third quartile is simply 19.583, if you like. So now we can compute the interquartile range. So we can say therefore IQR is equal to Q3 minus Q1, which will be 19.583 minus 8.125, which is 11.458. So interpretation, therefore the IQR of approximately 11.46 indicates the middle 50% of the data is spread across 11.46 units. And that's how that goes. But there's one more thing I like to talk about. There's one more thing I quickly like to talk about. Okay, or rather, I can make another video for this. Yeah, let me make another video for this. Okay, so this video is, I mean, it's already long, so I can make this into another video. So that's talking about role of interquartile range in identifying outliers. Okay, so thank you so much for being here up to this point. Watch out for how you can use IQR to deal with to identify outliers and to trim your data so that the outliers are brought to order, so to speak. Okay, so thank you so much for listening so far. If you have not subscribed to this channel, be sure to do that. Hit the notification bell so you can always get notified each time a new video is released. And don't forget to always comment, like, and share. See you next time. Bye.